Good day to all of you. Till now we have been discussing on modeling the DC-DC converter, and we have been discussing on the controller. We discussed about the PID controller and the block diagram and the various aspects of how a PID controller can be protected from anti-wind up and such issues. So, if you look at the block schematic in a bird's eye, the bird's eye view of the whole system looks something like this. This is the DC-DC converter. Now, this has an energy input, power input V in, power output V naught. It has two non-power ports, signal ports. One is the control input, that is where you feed in variation duty cycle, and another signal port, it is an output in fact, where the signals are sensed for feedback. This sensed signal does not contain or does not pass power, but only an information back to the controller. So, in this case it senses the output voltage and that is fed back and compared with a reference. The error is fed to a PID controller. Now, output of the PID controller is given to a pulse width modulator, and the job of the pulse width modulator is to convert the voltage which is on the input terminals to a signal which contains the information of the input signal in terms of time. So, the variation here is in terms of duty cycle. So, voltage amplitude to duty cycle conversion is performed by this PWM, pulse width modulator. So, let us look at what goes inside the pulse width modulator before actually performing the whole exercise of control in simulation or in hardware. So, let us take up the topic of pulse width modulation and then get back to the topic of control for the DC-DC converter. Now, if you take the pulse width modulator, the pulse width modulator is a black box. Let us say we give an input, we see a control signal. This is a control signal. Now, this has a nature with respect to time. We see is an analog signal. This is an analog signal. Now, the pulse width modulator takes such an input signal and gives an output, we shall call that as VPWM, output of the pulse width modulator. This is somewhat like a digital signal, discretized VPWM. This is converted to this type of signal where this width in time with respect to this width Ts, this is T on. So, T on by Ts, which is equal to the duty cycle, this is made proportional to Vc, to this waveform. So, that is the job of the pulse width modulator. An analog signal continuously varying is converted into a discrete signal which has two levels, either a high level or a low level. This is the low level, this is the high level, two states, and the time for which it is on in the high state, time for which it is off, that is in the low state, that is controlled and is made proportional to this analog signal. So, this is essentially what the pulse width modulator does, and let us see how this can be achieved. So, now let us take a very basic simple case. Consider an op amp. So, we have an op amp, as it is assumed that it has its supply. It has 3 terminals other than the supply signal terminals. One is minus, one is plus, and the output terminal. Now, let us say to this minus terminal, I give a signal Vt, and to the plus terminal, I give the signal Vc. And let us see what we would get at the output of the op amp. Now, what you get at the output of the op amp depends upon the natures of these two signals, Vt and Vc. Now, Vc is an input to the modulator. So, this is generally not under your control. However, Vt is under your control, and we want to make the output proportional to the output proportional to the input Vc, proportional in time, that is, the duty cycle is made, output duty cycle is made proportional to the input Vc. So, let us consider the following case. Now, let us draw waveform versus time. Let me divide the time into few cycles, each of period Ts. So, let us say we have these 3 periods here. Of course, these periods keep repeating, each of time Ts. Now, let us say that Vt is of the following form, pattern. It is a linearly rising waveform up to that period end, then drops down to 0 and again linearly rising. At the end of the period drops down to 0 and keeps repeating in this fashion. This is nothing but a sawtooth wave pattern. So, let us say that this Vt, which is a sawtooth wave pattern, is generated by some means and applied to this terminal here. So, to this terminal we apply something like this, the sawtooth wave pattern. Now, Vc is an analog signal, input signal, as we mentioned just previously before. Let us say it is coming from the output of the controller, a slightly varying analog signal, and let us say it has an amplitude less than the maximum sawtooth amplitude. Now, look at the points of intersection. In every period, we have the following points of intersection of Vc with the sawtooth or Vt. And let us mark that down. The points of intersection as indicated here by the violet line, violet dotted lines. Now, let us draw one more axis here. With respect to time, and let us plot V naught. So, remember that this green wave shape is nothing but Vc. The red wave shape is V naught, Vt. So, let me mark that in the same color as the wave shape Vt. Now, what is V naught? Now, go back to the op amp circuit. Now, this op amp is now acting like a comparator. Whenever Vc is greater than Vt, or whenever V plus is greater than V minus, V naught will go and clamp to positive maximum of the power supply, and whenever Vc is less than V minus or V plus is less than V minus, the output of the op amp will clamp to the negative of the power supply. So, if we say that the positive of the power supply is VCC and the negative of the power supply, the lower level of the power supply is VSS. So, you have two states, state 1 the higher state VCC, lower state VSS. So, let us see what happens. Now, at the left of the intersection point, this is the intersection point in this period. To the left of the intersection point, you see VC is greater than VT. So, VC V plus is greater than V minus, and therefore, the output will be clamped to VCC, the positive maximum. So, during this period, you will see that it is clamped to the positive maximum. This is VCC. And during the period, to the right of the intersection point, you see VC is lower than VT, V minus is greater than V plus, and then V naught will be clamped to the lower portion of the lower state of the power supply, which is, let us say it is 0. It could be anything other than 0 also. Anyway, for the sake of this graph, we will put it as 0. So, you have then again in the next cycle, you see that here VC is higher than the red, that is VT, and therefore, the output should be higher. Here. So, this will jump up, and to the right of the intersection of that period, you see that VC is lower than VT, V plus is lower than V minus, therefore, V naught clamps to a lower value. VCC, VSS, and so on. Every cycle, the situation is same. To the left of the intersection point, you will see that VC is greater than VT, and therefore, you will find the output getting clamped to the positive maximum of the power supply, and towards the latter part of the cycle, the output will get clamped to the lower part. However, what is interesting here is the intersection point itself. So, if you look at the intersection point, now this intersection point can swing anywhere from here to here. So, if you see here, let us say for example, I make the following modification. Let us consider the VC, which is having intersection at different points as shown. We retain the ramps, we retain the sawtooth pattern, only we change the VC. Let us say VC has a large amplitude in this cycle, a small amplitude in this cycle, and so on, like that, where the intersection points are now in this fashion. And you see that it becomes evident that when the intersection is at a higher value of the ramp, observe that the duty cycle is large, and when the value of VC is low, the duty cycle has dynamically changed to a low value. So, the point of intersection is actually the key in the pulse width modulator, which actually dynamically controls the on state. This is the on time, and this is the on time the next cycle, this is the on time of the third cycle, and so on. So, you see that the on time is large in this case, VC is larger, on time is small here, likewise VC is lower, so on time has increased again, the increase in VC. So, as VC is varying, the amplitude of VC is mapped to the on time, of the output, and this results in what is called as the pulse width modulation. So, what is actually being accomplished is modulating this width modulation, and as the amplitude is kept flat topped and reasonably constant, what you achieve, the wave shape, is a pulse, and therefore it is called a pulse width modulation, and in acronym form it is PWM. So, this is the basic concept of a pulse width modulator, which is employed in most switched mode converters, DC-DC converters, power converters. Now, let us go a bit more deeper into this pulse width modulator towards what you would see practically. Now, taking on from where we left off, now let us say we had that op amp, and let me now include one more op amp, and minus, plus, minus, plus. I am assuming that there is the power supply, and to the minus, let us give the sawtooth VT of the sawtooth shape, and let us give to one of the pluses VC and to another plus VD. Let us call it VD. And what do we do with the output? Let us OR them, diode OR them. So, this is called diode ORing, and the diode ORed output is called V naught. Now, what do we get out of this? Let us quickly plot the wave shapes and see what we get. Now, look at this across, let us say 3 time periods, switching periods like before. And we have Vt, they are sawtooths linearly rising and dropping down to 0 at the end of the cycle, linearly rising once again, and so on. This is our Vt. Now, let me draw 2 lines, and I am going to mark them as dotted. Now, this violet colored line, the low is marked as, let us say, Vd, and the green colored line I am going to mark it as Vc. So, you see that Vd has a point of intersection with the same triangle ramp, and Vc also has a point of intersection every period with the same ramp Vt, because Vt is given as a common minus input to the 2 op amps. So, now that we have drawn all the lines, markers, let us take one axis, another axis t, and try to plot V naught . Now, for this Vc, what is V naught? Now, V naught now if you take Vc here is greater than Vd, and therefore, even during the time when Vd is low, okay, let me make a small modification here. Let us have some more clarity. Let me plot first this as 1, 2 and 3. Now, let us plot 1. The output of op amp at 1, you will see that it has a wave shape something like this. Now, this is how the wave shape would look at the output of 1. Now, let us plot what it would look like at 2. Here, it is with respect to this input Vc. So, as you see we are now taking the intersection corresponding to that of Vc. And then what is V naught? 3. V naught is nothing but ORing of this wave shape and this wave shape, which is nothing but this wave shape in this case. So, V naught is nothing but this itself. This itself is your V naught. However, the issue would crop up when, what happens when Vc has gone below Vd. Look at this, I am carefully drawing this. Vc has gone below Vd, which means let us take out some of these confusions. We will redraw them, of course. What would happen to the output? So, I am going to redraw some of these. Okay. Notice that the Vc intersection is smaller, occurs at a lower part of the ramp, and the output of 2 is limited to a small pulse like this. And what is 3? Now, 3 is nothing but ORing of 1 and 2. 3 becomes same as 1. So, this may vanish, but still V naught will remain at this value. So, what do you take away? What we see here is minimum pulse width. In most of the switched mode power converters, the switches are nothing but power semiconductor devices. Now, the power semiconductor devices cannot switch at very low pulse widths. There should be a minimum pulse width given to the power switches of the switched mode converters. Otherwise, there will be pulse skipping and other undesirable effects. Therefore, in most of the pulse width modulators, a minimum pulse width is decided and fixed. So, even when the input signal goes to a very low value, which results in a very small pulse width, the Vd portion of the op amp, which is ORed together here, will ensure that the output pulse width does not go below what is decided by Vd. So, that is an important part of your pulse width modulator to fix the minimum pulse width that can be applied to the power semiconductor switches. So, next let us see what we try to achieve. So, this is one aspect. Let us go further from there and try to put in the entire. We saw that we have two op amps with diode O-ring and these two op amps resulted in kind of a pulse width modulated output. Now, let us say we have another black box and out of the black box gives Vt, the sawtooth wave. Most of the cases the sawtooth wave is generated by means of timings that are set by two components, a capacitance and a resistance, the R and the C, the RC time constant of which determines the period of the sawtooth. And then we shall call this as Vd and let us say we have Vc. Vc is the control signal coming from the output of PID. Vd is called dead time control or just say minimum pulse width control. So, for the moment we will call this as min pulse width. So, now the output of this we know is a pulse width modulated circuit, but there are many circuits like the push pull, like the full bridge, like the half bridge, where you need to give pulses, PWM pulses to the two switches which are complementary. They are not 180 degrees, exactly 180 degrees complement. They are not in fact supplementary, they are actually complementary, as you would see. We would like to give a pulse something like this. Now, if you are having a full bridge circuit composed of two semiconductor switches, let us say IGBTs, and now let me call this one as V gate A, V gate B. Now, we would like V gate A to be of this fashion, and we would like V gate B to be something like this. So, see that V gate B is not an inversion of V gate A. V gate B is complementary to V gate A, occurring at a time when V gate A is fully off, but there is also a gap, a common time when both are off. This is necessary because all these power semiconductor devices are practical devices. They need a finite time to switch on and switch off. So, when one of the transistors is on and the other is off, you need to give some specific time. This is called the dead time, and during which time you are allowing the on transistor to turn off, you are allowing the off transistor to turn on without having an overlap, or therefore a shoot through, current shoot through. So, in order to have such safety, we need to provide some time where both do not get a gate drive, do not get a gate drive pulse. This is the type of output that is needed by most of the power semiconductor devices, drive signal. Therefore, let us see how the raw pulse width modulated wave shape is modified to something of this type. So, if it is for single ended output, just only this any one of them can be utilized. If it is for double ended, switching both two complementary pairs, you need to use both these gate signals. So, continuing from where we left off, let me take this portion alone. And paste it here. Now, to this circuit, let us add a flip-flop. Now, let me put a toggle flip-flop. This is a T flip-flop. You have Q and you have Q bar. Now, the output of these two go to two AND gates. And out of those two AND gates go to two NOR gates, as shown like this. Now, look at what is going to be done. From here, the input, you draw a line and give it to the other inputs of these NOR gates. And the other inputs of the AND gate is brought out, and we will call it as a steering control, or we will just call it as S bar P, series or parallel, and let us see what it means. or it could be in single ended or push pull mode for dual drive, complementary drive. So, when it means yes, when S is S bar P is 0, these AND gates are disabled and nothing from this toggle flip flop is going to affect here. So, this is 0, and what you get directly from this output is steered to both these OR gates, and you would get exactly similar waveforms here except that they are inverted. When this is equal to 1, so that is when you have the push pull mode or complementary mode. Now, let us see what happens to the various waveforms, and the output of this in general is given to two bipolar transistors, and they are brought out. So, now let us start with the waveform at 3. We know that waveform, this is 3. If you go back, we had named it as 3. So, we will again call it as 3, start from there, and what you had at that point is pulse width modulated waveform, something like this. Now, what is obtained at Q? Q, this is a toggle flip flop. At every positive edge, the toggle flip flop is triggered, and you would get a change of state. So, let us say we get a change of state at this positive edge, you have another change of state, at this positive edge you have another change of state, so on. And likewise Q bar, Q bar is nothing but an inversion of Q. This is exactly 180 degree inversion of Q, no dead times here as such. Comes in this fashion. Then let us see what is the, now because S bar P is 1, these AND gates are enabled, the Q and Q bar signal go directly to this point, the OR point. The signal, this signal is ORed with this and inverted. So, ORing of this and this signal would mean like that, and like that. ORing and inversion. An inversion would mean a direct inversion of this. Therefore, I am going to write, I am going to remove this and write the NOR signal. Which is like this. This is at base 1. Likewise, base 2 is the complementary output. This I will call it as base 1. Now, here this is ORing of this signal, ORing of this signal, you see here, with Q bar, what comes at Q bar here. So, Q bar is now ORing of this and take an inversion would give waveforms like this and so on. Notice that B2 and B1 are complementary, there is no overlapping zone, and we have the dead time. So, as this is varied, this pulse width varies. As this pulse width varies, you will see a variation in the pulse width here. Likewise, a variation in the pulse width here for the B1 waveform. So, as this varies, this will vary. So, this gives you a pulse width modulated complementary signal. So, in fact, most of your pulse width modulators have this kind of a basic structure, which would give you possibility of two complementary signals, possibility of having the steering line when it is made 0. The output is the 0.3 output is directly brought to the output, an internal ramp, an internal power supply. So, there are many pulse width modulators available These are available as pulse width modulator ICs. One very common pulse width modulator IC with this structure which we use is TL494, SG3524 and many more. Okay. So, the pulse width modulator in short can be put as a VC as the input and the output which is the PWM. Notice that there are two possibilities. because most of the outputs of the pulse width modulator have an output stage and both the emitter and the collector are brought out. So, if you connect an external circuit in this fashion, or if you connect an external circuit in this fashion, there if you take VPWM from here or you take VPWM from here, both will definitely give a PWM output, pulse width modulated output. However, there is a 180-degree inversion between this PWM output and this PWM output, because here you are taking it from the emitter, here you are taking it from the collector, which results in a 180-degree output. So, you have to be careful and count the number of phase shifts that you have within the loop in order to have an overall phase shift proper for closed loop negative feedback. Keeping that in mind, now this has to be brought into focus for our overall closed loop picture that we had, which is the controller, the PI or the PID, followed by PWM, the modulator, and which is connected to the DC-DC converter. The output feedback is fed across to this. You have the V naught reference, error, output of the PID is called VC, and output of the PWM is VPWM. What you have here, the waveforms analog signal, and what you would have here is pulse width modulated kind of discrete switching signals, and this information is fed to the DC-DC converter. Basically, the control signal information is fed into the DC-DC converter as a switching pulse width modulated signal. Okay. So, this of course is our complete control block diagram. So, we have seen the various aspects of the block diagram. We have seen how to model the DC-DC converter. We have seen how to model the PID controller, and we have also had a discussion on what a PWM modulator is or how it looks inside. Now, in the following classes, we will try to look at this whole control system block diagram as a whole and see how we can design this, and also how we can rate this and simulate this to get a better insight into the whole system. Thank you.